Here are the notes for page 82 on using the second derivative test to find local extrema. Remember, local extrema is our local max and min. So the first thing we're going to do is write down their conditions in order to use the second derivative test. And those are: suppose f double prime is continuous on the interval with c in that interval. And we also know that f prime at a particular c is equal to 0. What we know is that if f double prime at that same c is greater than 0 or positive, then we know that f has a local minimum at c. Now it's not hard to remember. Remember, what we do know is that f double prime is positive means that it concaves up. So what we're finding is that we're going to have f of c down here. So we're going to find that that is going to be a local minimum. Likewise, if f double prime of c is less than 0 or negative, then we know that f has a local max at c. And again, remember, if f double prime is less than 0, it is concave down, so our point must be at the top, therefore it is a local max. However, if f double prime of c equals to 0, then this test doesn't tell you anything. So the test is determined to be inconclusive. So it doesn't tell you anything about the extremas. So let's use this in example number 1. Our job is to find the local extrema. Remember, extrema is local max or min for f of x, where f of x is equal to sine squared of x. So the first thing we're going to do is we're going to find when is f prime equal to 0. So we're going to go find those c values. So the first thing we need to do is find f prime of x, and we found that to be at sine of 2x. We found that in our review. So the question is, when does this equal to 0? So we're trying to find sine of what angles equal to 0, or think of it as 2x is equal to the inverse sine of 0. So the easiest things for me to do is to do it this way, and we find that our angle, so I'm going to call it theta for right now, that our angle is when it's equal to 0, when it's equal to pi, when it's equal to 2 pi, 3 pi, etc. every time it's a pi. But now what we want to do is that theta is actually 2x, so I'm going to have 2x is equal to these guys. Now when we want to find x, we're going to find that that happens when x is equal to 0, when x is equal to pi over 2, when x is equal to pi, etc. So 3 pi over 2, and it goes on. So one way we can write this is that this happens every time we have a pi over 2, and then we have some number. And that number can start off at 0, and then 1, 2, 3, etc. So we can see that if it's 0, I'll get the first one, 0. If I have 1, I get pi over 2, which is this one. When I put in 2, I get 2 pi over 2, which is pi, so I get this one. So it's generating all the possible solutions. So we have found that. So the next thing we need to do, sorry about that. The next thing we need to do is to find f double prime. So let's go find f double prime of x. And we did that, and we said that was 2 times cosine of 2x. So what we want to do now is going to plug in these x values that we found. So let's find f double prime at 0. So that'd be 2 cosine of 0. Cosine of 0 is 1, so this is equal to 2. And notice that is greater than 0. So what we have found, since it's concave up, we have found a local minimum at x is equal to 0. The next one we know at f double prime at pi over 2 is equal to 2 cosine of 2 times that is pi. Cosine of pi is -1, so this becomes a -2, less than 0, which means it's concaving down, and we have found a local maximum at x is equal to pi over 2. And we could do the same thing for the next one. F double prime at pi is equal to 2 cosine 2 times pi, which again we'll find that to be 1, so it's 2 greater than 0. Again, it's a concave up, so we have found a local minimum at x is equal to pi. So I'm going to stop right there. You can kind of get the idea of what's happening. We can actually find actual points. So actual points would be our local minimum would occur at 0 when x is equal to 0 right here. So we're going to plug that into f. F is sine squared of x, so I plug in 0, so sine of 0 is 0, so that's going to be 0, so that's going to be one of our points. Another local minimum is at pi, so I'm going to plug in pi, so sine of pi is 0, squared is still 0, and we can keep on finding those. And we also found a local max when x is equal to pi over 2. So I'm going to plug in pi over 2 and sine squared. So sine of pi over 2 is 1. We square it, it equals to 1. And again, we can keep finding more and more of them. So I just wanted to know at least the first 3 starting from 0. So that's what we found. Okay, so one thing that might be very helpful when we're going to be graphing is this table here, and I'm going to have you draw that. So we're going to see if we can get a square or close to a square, and we're going to divide it into 4 quadrants. And up here I'm going to put f prime of x. Over here off to the side I'm going to put f double prime of x. And up here I'm going to put positive, and over here I'm going to put negative, put positive, and I'm going to put negative. So what we find is that if we have f prime is positive, remember that's slope, it's increasing, so it's going from this going upward. And if at the same time we have concavity is positive, it's going to be concave up like this. If we had the same increasing scenario, because the slope is positive, but we have a concavity down, then our graph kind of looks like this. If we find that our slope is negative, so I'm going to have start at a high point, finish at a low point, but our concavity is still concave up, we're going to find this part right here. So I used to tell my students concave up is like a cup, so it needs to hold water. If we still have our decreasing, but it's concave down, it makes a frown, so that's this guy right here. So these are going to be very helpful when we're trying to create our graphs. We're going to use both page 83 and 84 to do example number 2. I just want to make sure you have enough space for all the information that you want to write. So we're doing graphing functions. So in example number 2, our job is to graph f of x, where f of x is equal to e to the negative x squared. So the first thing we're going to do in our 9 steps of graphing is make sure we understand what is our domain. In this case, because it's exponential, our domain is going to be from negative infinity to infinity. And don't forget those parent functions are going to come in handy. The second thing we know is going to be by using symmetry. In symmetry, I just want to remind you that you want to look at your function to see if it's even or odd. So if it's even, we say we have f of x is equal to f of negative x. What does that mean in terms of a graph? It means that if I was looking at a graph like this, here's x and here's my y value, that if I plug in negative x, I get the same y value. So in our case, let's take a look. So let's pick in a number. I'm going to pick 3 because 3 is my favorite number. So I'm going to pick 3 and negative 3. So I'm going to plug it in to my function and see if we get the exact same thing. So when I do that, I'm going to have, if I plug on this side, I have e to the negative. I get my 3 and I square it. That's 9. If I do the other side, I get e, I have my negative, and I have negative 3, but negative 3 squared is a positive 9. So notice we get this same thing. Our graph is actually even. So that means that what we see on the left side of my graph, we should be seeing on the right side of my graph, whatever it may be. If a function is considered odd, that's when we have f of x is equal to a negative f of negative x. Now, what does that mean in terms of our graph? It means that we're over here at x and we have some positive y value. When we come to negative x, we get a negative x value. So we can see we're going to have one positive, one negative because of the x value being negative. Those you might see something like this. That is considered an odd function. But we noticed that ours was even, so we don't have to worry about it being odd. But that's how we check. We can actually just plug in values, and it doesn't matter what it is as long as you plug in the positive and the negative. Stay away from 1 and 0 when plugging in numbers. Those are special cases, so try to stay away from them. The third thing we're going to do is go find some derivatives. So let's go find the first derivative and the second derivative because we're going to be using both the first derivatives and the second derivative tests. So if f of x is equal to e to the negative x squared, remember we can think of it as u is equal to the negative x squared, so we have e to the u. We need to take the derivative of u, so I'm going to bring down negative 2x to the 1 power, so that's true, and then our derivative is going to be e to the u times du. So for f prime of x, we're going to see that the derivative of this is itself, e to the negative x squared, times the derivative of our exponent, which is negative 2x. So I'm going to rewrite that as negative 2x e to the negative x squared. So the next thing we need to do is to find the second derivative. This is f prime of x. Second derivative, we're going to have to use the product rule. So we're going to use this one as u, this one as v. So f double prime of x is going to be u dv. Well, that's the derivative of this. We know that. That's going to be itself, e to the negative x squared, times the derivative of the exponent, which is negative 2x, plus v, which is e to the negative x squared, and du, the derivative of that is negative 2. So notice how I put that negative in parentheses to remind myself I'm still multiplying. So f double prime of x is equal to positive 4x squared e to the negative x squared. That's this first term. Minus 2e to the negative x squared. Just to see if it kind of makes things a little simpler, let's see if we can factor. We notice that both of them have a 2 and both of them have a e to the negative x squared. When I do that, I end up with 2x squared minus 1. So that might come in handy when we're trying to find it equal to 0 and stuff. So the fourth thing we need to do is go find critical points and possible POIs. So to find critical points, remember we need to find f prime of x, or c. We got to go find those c values. when it's equal to 0. So we're going to get our f prime, which was negative 2x e to the negative x squared, and decide when does that equal to 0. So remember we said that one of the things that might help is if we went on ahead and put them in numerator and denominator format. So negative 2x, at the bottom I have e to the x squared. At the top, that happens when x is equal to 0. At the bottom, because this is an exponential, it'll never equal to 0, so it'll never be undefined. So this is the only critical point we have. To call it a true critical point, remember it is a point where x is equal to 0 and I plug in 0 into my f. So when I do that, I get e to the 0 power, which is 1. So this is our point on our graph that we can plot. That's good to know. We want to make sure we plot that. So the next thing we need to do is also go find out when does f double prime of some c is equal to 0. Remember, this is to find possible POIs. They're not guaranteed, but they're possible to find those. So let's do that. So we have 2e to the negative x squared times 2x squared minus 1. Again, I'm going to put that in fraction form. So I have 2x squared minus 1 over e to the x squared. And the question is, when does that equal to 0? Again, at the bottom, it'll never equal to 0, so we won't have that undefined situation. But at the top, we're going to have that 2x squared minus 1 can equal to 0. So we're going to solve for x in that case. I'm going to see that I have 2x squared is equal to 1, x squared is equal to 1/2. Then x is equal to plus or minus the square root of 1/2. Or plus or minus the square root of 2 over 2. Now, you can leave it like this, or you can leave it as plus or minus 1 over the square root of 2 instead of rationalizing the denominator. I'm used to rationalizing the denominator, and that's the reason why you see this value. Moving right along. For step 5, our job is to find increasing, decreasing intervals as well as concavity intervals. So we know how to do that. First thing we need to do is to make sure we have already found our critical points. So let's start off with increasing and decreasing intervals. So we're going to start off with our number line. So I'm going to put my number line way up here. We're going to go from negative infinity to infinity. And the only one we found was 0. So let's go on ahead and test some points. So we are going to test negative 1 and x is equal to positive 1. And we're going to test it in f prime, because remember, f prime will tell me slope. So we got to make sure we remember what f prime is. In our case, f prime is equal to negative 2x e to the negative x squared. So when I plug in any value here for this portion, it's always going to be positive, no matter what we pick. Remember that negative exponent just brought it down, but it's still positive. So this is always going to be positive. So the question is, what happens here when I plug in our values? So when I plug in negative 1, f prime of negative 1, remember we're not looking for a number, but we can find it. I'm going to put in a negative 1 here. I have negative 2 times negative 1 is a positive 2 times this positive number. So when I do that, I actually find this to be positive. When I plug in x is equal to 1, again, I'm finding f prime of 1. We know that this part, I'm going to plug in a 1, I get negative 2. And then this part is always positive. So when I multiply, I'm going to get negative. So that's good to know. Right underneath, so we have found increasing interval from negative infinity to 0 and decreasing interval from 0 to positive infinity. So if this one's going up and this one's coming down, we know that when x is equal to 0, we have actually found a local max. You can actually find that value of that point by plugging in 0 into f. When I plug in 0 into f, I get e to the 0 power, which is 1. So this is our local max. And I'm going to make sure I box that in and use it in my graph in a few. Alright, so let's go think about concavity intervals. Again, we're going to have our number line, and look what I'm going to do. I'm going to match it up so it looks the same as this guy right over here. I'm going to put a 0 here, but kind of light, because we really don't need that. That wasn't part of our situation when we were looking at f double prime. When we did possible points of inflection, we found one of them. Here's negative infinity, here's positive infinity. We found one of them to be negative square root of 2 over 2, and the other one to be positive square root of 2 over 2. Okay, so just so that you know, this one's about negative 0.7 and this is about positive 0.7. So that way we know what to test. So we're going to test. We're going to pick, we need 3 numbers. We need one number here, so we're going to pick x is equal to a negative 1. We pick a number between here and here. 0 sounds good. And then we pick a number between here and here, and we're trying to x is equal to 1. But remember, we're going to test it in f double prime of x. And f double prime of x, remember, we found that to be 2e to the negative x squared times 2x squared minus 1. And again, from knowing that this parent function is always going to be positive because it is exponential, so we know this is going to be positive. We just need to determine if this is going to be positive or negative. So if I plug in negative 1, I square it. That's going to give me 1. 1 times 2 is 2. 2 minus 1 is a positive 1. So I get positive times a positive when I plug this in. So f double prime of negative 1 is going to be positive times positive, which is positive. Remember what that means. That means we have a concave up. So something like this is happening here. When we get in x is equal to 0, we're going to plug that into double prime. And again, when we do that, this part is going to be 0. I get 2, which is a positive number, which we knew that. It was always going to be positive. Over here, when I plug in 0, I get 0 minus 1. I get a negative. So we see that this is negative. So here we find a concave down is happening. When I plug in x is equal to 1, I have f double prime of 1. And again, we're going to see that this is always going to be positive. If I plug in 1 here, I get 2 minus 1. That's also positive. So positive times a positive is positive. What that means is we have a concave up. So if we take a look at what we have, and I'm going to bring these both together. So here's my number line, and what we have is negative infinity and positive infinity. Then the next thing we see is we have 0. We have a negative square root of 2 over 2, and we have a positive square root of 2 over 2. If we test it, so here's f prime of x, and this is what we found. So at x prime, we found that it is positive here in this interval. It's positive here in this interval. It's negative here in this interval, and it's negative here in this interval. That's from the first number line that we have. If we look at f double prime of x, we're looking at the second one. We found that it's positive here in this interval. We found that it's negative here and here for this interval, and then we found that it was positive in this interval. So when we go back to our picture, the one that we drew that had positive and negative, so this guy right here, just to remind you, we said that we had positive, positive, negative, negative. This is f prime and this is f double prime. What we have is when they're both positive, so increasing and concave up. So what we know from here to here is that it's increasing and concave up. From here to here, we know it's still increasing, but it's concave down, so it's doing this. From here to here, it's decreasing from here to here, and it's concave down, so it's still doing this. And if we're looking right here, we're going to find it's decreasing and it's concave up, so it must be going like this. So somehow or another we got to get all of these to be continuous, because our function is continuous from negative infinity to positive infinity. So now we need graph paper. So we can start graphing. What we need to do now is also find our extreme points and our POIs. So step number 6 is to find extrema points and POIs. Well, we already found extrema points. That was going to be our local max, and we said that one was at 0, 1. So we're going to put that point in our graph. For POIs, remember that's when the concavity changes, and we can see that from this graph up here, that concavity changes here and here. So those were our two concavities. So our POIs are actually found when x is equal to a negative square root of 2 over 2, and the other one is when it's positive square root of 2 over 2. And we got to stick that into F to find these values, these y values. So I'm going to let you verify the math, but we're going to find that it's going to be 1 over e in terms of y values. And again, we can use our calculator to estimate what that value is. Again, because we know it's even, we know we were going to have the same y values regardless of which one I plugged in. So we have found our points of inflection. So the next thing we need to do is talk about stuff on our graph, such as asymptotes. We don't have any in our case, but we would make sure that we want to write those in if we had them. So we don't have one because we don't have any in our denominator. So we don't have any vertical asymptotes or horizontal asymptotes. So we're going to say none in our case. The 8th thing that we want to do is look at intercepts. Intercepts remind you that you want to find the x-intercept and the y-intercept. So let's find out what happens when x is equal to 0. We already know what happens when x is equal to 0. That's equal to our maximum, and that is our y-intercept. When we want to find the x-intercept, we let x equal to 0. I'm sorry, we let y equal to 0 and solve for x. And we're going to find that that never happens, so there are no x-intercepts. And again, what we're doing is we're getting our f of x. Our f of x, remember, is e to the negative x squared, or 1 over e to the x squared. And the question is, when does this equal to 0? Well, like we said, we would let the numerator equal to 0, and that will never equal to 0, so we have no x-intercepts. So, like I said, we need graph paper now, and I'm just going to put it on here and tape it on one side so I can still see the information underneath. So let's plot our points. What we do know is that 0, 1 is our maximum. So we graph this one and our y-intercept. Our point of inflections are going to be at 0.7 and some value less than 1, and again 0.7 less than 1. According to our concavity, we should see something from over here coming up until we get to here, and then concave down, and then concave up going this way. So you can look in your graphing calculator. That would be step number 9, is to see if that can help you in terms of graphing. So this is step number 9, which is to graph. And that concludes the video for graphing functions using the first and second derivative test.